So for this module, we'll look at the basic units that we'll be using throughout the course, along with how to convert between them. You're probably familiar with the fact already from your prior science or engineering courses that as engineers, we'll be forced to work across two units, both the metric system or international system of units, or abbreviated SI units, along with the US customary system, which we'll see in some of our text tables is abbreviated as FPS, or foot pound second system. So just a little bit of notes about the system. It's not really a kind of learning objective of the class, so I don't want to spend too much time. You're probably familiar with the U.S. customary system being inherited from kind of the British or empirical system, and a lot of the kind of definitions of particular units being defined according to standards that are kind of hard to replicate. So think back to the idea of how a foot as a measure of length is defined. Versus the SI system, which really has two advantages, one of which is kind of the standard definition. For a lot of the units, it's kind of something that can be replicated empirically in terms of the fundamental unit of distance, the meter. It's defined in the SI unit system based upon the propagation of light in a vacuum. That's something that you can kind of standardize and measure across locations. The other real advantage of the SI system is if, again, in statics, we're working across a wide variety of size of application domains, from the kind of microscopic scale to the civil engineering scale. So one set of units is not going to be good enough by itself. What the SI units system gives us the ability to do is to scale those units to different sizes using metric prefixes, as we'll see a little bit later in this lecture. One thing that I wanted to mention that's emphasized quite heavily in your book is that when you have certain fundamental units that are defined according to some standard, like the unit of length or the unit of mass or the unit of time, when you introduce equational relationships between them, things like Newton's second law, that will inherently restrain the units of one quantity. They will be derived in terms of the definitions for the units of the other quantities. And we'll look at an example of that in a table on the next slide. So here are, for the four fundamental quantities that we defined in the prior learning module: length, time, mass, and force. Notice that in the international system, we use units of meters, seconds, and kilograms, respectively. And the unit of force, as denoted by this kind of subscript asterisk, is actually derived in the SI unit. Namely, what is a Newton? Well, if F equals ma, then the Newton should take on the units of the product of mass times acceleration. Of course, mass measured in units of meters. That's where, I should say mass measured in units of kilograms. Be careful with that. That's where the kilograms come from. And the units of acceleration. Acceleration is the second derivative of position. Each time you take a derivative, you get a unit of 1/seconds in there. So position is where the meters comes from, and the two factors of seconds comes from the second two derivatives that are needed in order to compute acceleration. In contrast, in the US customary system, it's the foot, second, and pound that kind of have a standardized definition, and the unit of mass, which is the slug, is derived from them. So one thing you need to be able to do whenever you're working across unit systems is convert between them. We'll do an example through dimensional analysis that I'm sure you've seen before. But for our class, we'll need these conversion factors quite often. Namely, 1 pound is 4.448 newtons. And you can read the remainder of them. May be good to kind of commit just to have some physical intuition of what a newton of force looks like, some kind of this relationship between pounds and newtons. You probably already have kind of a fundamental idea of what a meter is. If you convert this back the other way, just approximate 1 foot as 3/10 of a meter, reverse it, and that means that 1 meter is about 10/3 of a foot, or 3.33. You probably remember that a meter is about a yard, a little bit bigger than 3 feet. So it just gives you, when you're working these problems, even though we don't have a lab component, it's good to have some kind of physical intuition of the size of things that you're dealing with, where it's feasible to do that. So let's look at an example problem. Say we were given a quantity 2 kilometers per hour, and we wanted to convert that to meters per second. And I'm going to write this one out on the dot cam. But I did, as I'll show you in a minute here. Sorry, I'm a little bit under the weather today. So I'm kind of behind the 8 ball trying to get all these courses up and running anyways, and then to be sick is really tough, but not complaining. We all have challenges in our life. So here's the actual type solution, but I want to show you by hand here, just so we can work through it together. Let me go to my .cam. Go. So how do you do? So we were given this quantity, 2 kilometers per hour. Well, first of all, let's ask ourselves, what is this? It's easy to, when you're working these problems, just turn them into a pure mathematical thing and lose track of physically what we're talking about. So units of distance divided by units of time. What this is a measure of, most fundamentally, speed or the magnitude of velocity. And I'm kind of using one definition to define another, so you might ask yourself, well, what do you mean by that? Well, it's a description of how quickly a displacement is happening in time. In 1 hour, this object, whatever we're describing, undergoes 2 kilometers of displacement. So what we want to do is convert that to an equivalent representation of speed or magnitude of velocity in meters per second. So how are we going to do that? Well, the concept of dimensional analysis basically says that we can always convert a quantity given in any unit to another unit that we want, in this case meters per second, if we multiply by conversion factors, and I'll show you what I mean by that in a minute, but which are basically ratios. Sorry, that's a little bit hard to read. Let me cross it out. Sorry. It's been a while since I've had to write on the .cam. Conversion ratios are ratios where the top quantity is equivalent to the bottom quantity. And we don't mean that the number is the same. It's not equivalent like in a mathematical sense. It means we're describing the same thing. It's just 2 different ways to write it. So here, we need to take our distance measure, or our length measure, from kilometers to meters. So we need a conversion factor that tells us basically for a given amount of kilometers how many meters it is. And usually these are things that you would look up from a table, but here this is a relatively easy one to do because we know that in the metric system, as we'll see in the next slide, the book's kind of weird. It uses this before it introduces it. Kilo is an abbreviation for multiplying by 10 to the third. So I can just rewrite K as 10 to the third. And 1 times 10 to the third is just 1,000. So what this tells me is that 1 kilometer and 1,000 meters are the same thing. So if I write them as a ratio, effectively, if I were to multiply by that ratio, I would just be multiplying by 1. So you might ask yourself, well, how should I arrange my dimensional analysis ratio? Well, when you multiply, you can kind of view the units as common factor type quantities that you can cancel. So I'm going to, in my conversion factor, place the description of kilometers in the denominator, that way they will cancel, and place the meters in the numerator, that way I can retain them. So what is my conversion factor? Well, 1 kilometer is equal to 1,000 meters. Now the next thing that I need to do is get rid of units of hours and convert to units of seconds. So I need to know a relationship between hours and seconds. And I'm showing this as 1 step. You can show it as 2. I think I did that in the slide. But the question is, on the time side of things, what is the relationship between hours and seconds? Well, let's just use the fact that 1 hour is the same as 60 minutes, and 1 minute is the same as 60 seconds. So I can actually show this as a 2-step process, as I was saying. 1 hour per 60 minutes and 1 minute per 60 seconds. And kind of using that same concept of canceling units along the diagonal that I spoke of previously, I can derive the fact that 1 hour is 60 squared seconds. That is kind of a conversion factor that I can use above. So I'll go back to the top and I'll type in 60, 60, 1 hour is 60 seconds squared. And, how did it's good that I made that mistake, because you can kind of make sure that you're catching yourself in your math correctly. Clearly, an hour is a whole lot of seconds. So if there's 1 here, there better be a very large number there. Make sure that your dimensions are adequately canceling, which they are, and just go through and do your computation. First of all, check what will the units of this be. If you've done your dimensional analysis chain correctly, there should only be 1 unit remaining in the numerator, which there is, meters, and only 1 unit remaining in the denominator, seconds, which there is. And just do the math. 2 times 1,000 is 2,000. In the denominator, we have 1 times 1 times 60 squared. So let's see what that math turns out to be. Unfortunately, I don't have a calculator up, so I have on the slides already done this computation, and it comes out to be 0.556 meters per second. Now, one thing I want to bring up is you might ask yourself, why didn't this is an example from the textbook, why didn't they actually convert that further and use another prefix? Maybe you when you see this naturally say, oh, I would prefer to write that as 556 millimeters per second. And we'll deal with that idea of engineering notation in the next learning module. However, for these type of examples, we were asked to use this unit of meters per second. And although when we actually made the computation and found out how much 2 kilometers per hour was in meters per second, our resulting coefficient was type somewhat small, meaning that this unit may be a little too big. We're going to leave it like that just because we were asked to report our result in meters per second. So we weren't given any guidance on actually reporting significant figures. But as we'll see in the next lecture, there is meaning in the amount of digits that we're displaying here and the corresponding rounding that we did to get there. So hopefully that shakes off some cobwebs as it relates to doing unit conversion through dimensional analysis. And remember that in this course, we'll be working with 2 sets of units, the traditional US customary units and the SI system.